Yeah, okay. So yeah, we started to introduce the idea of big O notation. And the idea here is you look for the dominant part of the growth function. So here, if t of n is 17, well, there's no dominant part. It's 1. We see the n here. Well, that's linear. We don't care about the -4. We don't care about the coefficient. It's n. 12, don't care about the 12. So we see n times log n. And then something with an n. Well, n times log n is worse than linear. N squared. 2 to the n? 2 to the n is bad. And then we had a little bit of like a quiz here. Well, n squared, n cubed, n log n cubed, 2 to the n. There we go. The trick is, if you look at something like this, you go straight for the biggest coefficient. Yeah, I mean, there's more to it because you've got logs in there. But yeah. And by the way, usually, almost always in computer science, whenever I say log, I always mean log base 2, not log base 10. Log base 2, so divided repeatedly by 2. Why 2 to the n over n to the 100? Because 2 to the n will, I'm pretty sure 2 to the n is worse than n to the 100. Pretty sure. Eventually. Either way, both are terrible. I mean, you can verify that, check if I'm wrong. Okay. So, deriving growth functions. So we learned how to go from t of n to big O of n. But where the hell did t of n come from in the first place? Why are some worse and some better? What do you, I'm not sure what you mean. Why are some worse and some better? Why is n cubed worse than n squared? Because it, like, the shape of that growth, it grows faster in terms of the amount of time it would take. If you plot n squared and n cubed, you would see the rate of growth of n cubed will be a lot faster than n squared. Anything to the n is worse than n to the anything. I think so, yeah. All right, yeah, so how the hell did we get the t of n? All right, so for simplicity, we are going to pretend some constant time statements take 1 unit of time of work, when in reality they might take more, but this is safe to do since constants are being ignored. Meaning, if I say something like x plus y, I would say, well, that's like 1 unit of work. Even though really there might be more going on in the background, it might be like, oh, it takes like 7 steps or something. Yeah, but it's like 7 is just like a coefficient, so we don't care. Like, we don't care about the constants. We just pretend everything's order 1. So just as a warning, stuff like this might not actually be 1 step of time. It's just we're treating it like that for simplicity. All right. What about MB? What? What? All right, I'm gonna move on. So, growth function. If we see something like this, well, t of n is like, oh, there's like 3 units of work there. So like it's order 1, right? Like 1, 2, 3. There's nothing, none of this code depends on some like value of n. It depends on values of x and y, but those are just like constants. It's not like, oh, okay, well, go look through a list of size n. Well, how big is n? Well, how big do you want to make it? There's no n here, right? So t of n in this case is 3, meaning code like this is constant time code. This code isn't going to run any longer or shorter if we have a bigger n, because n's not even a factor here. But when we see loops, it starts to often, well, assuming the loop depends on some size n, this is where we start to see n pop up. So if we look at this code here, we can look at this and be like, well, this is like 1 unit of work. All right? And then we can look at this loop here. This is a for loop. Well, what is this loop doing? Well, this loop is doing 1 unit of work. But how many times is this loop going to run? How many times am I going to do 1 unit of work? Someone type it in the chat. Someone. It's not a trick question. This loop runs how many times? Thank you. 1. No. Infinity. No. N. Wait, you guys are, I don't know where your head is. You're working too hard. This loop runs from 0 to N. What's N? N is whatever. N is a number. So if we do one unit of work N times, well, that's 1 times N. So we have a growth function that would look something like 1 plus 1 times N, which, okay, we just look at the N. So, oh, that's big O of N. How do we identify N? Right here. I realize it's like, well, what if it was like dot length? Like some array dot length. Well, it would be like the length of the array. N is usually like the thing that, like if I'm doing linear search, N would be how long is the list that I'm searching through. N is the thing that when it changes, the growth function will change as a consequence of that. We set N, right? Well, it would depend. Like, are you searching through a list of size 1 billion or size 1 trillion? Define N. Well, that could be like, yeah, the length of a list. How many things are in my stack? No, we define it. Kinda, yeah. I mean, if the list is size N, I mean, did I make the list size N? Well, someone did. Okay, so we can think of a loop and a line and a number line, okay? Every time the loop runs, we put our finger on the next number. So like, I always think like this, okay? I start, the loop goes to 0 to N minus 1, right? So I go, okay, I have to put my finger here, and then here, and then here. How many things do I have to put my finger on? All of them, all N of them. So this is like order N. And then when we see nested loops, this is where things can get a little tricky. But there's no secret trick here. We're just following the same rules over and over. So outside the loops, we have 2 units of work. And if we go down here, we can see that 2 right there. And then we've got a loop. And then inside that loop, we've got this loop. Oh boy, okay. So, well, this right here is 1 unit of work. But how many times am I running that 1 unit of work? N, exactly, right? So I'm running this right here. This is order N. And then before that, though, I've got another 1 unit of work. So this is like 1 plus N. But how many times am I doing all of that, though? N times. Notice that? Like N times. If you're wondering why is it multiply and not plus, well, plus is like if you have sequential steps. Times is if you have like, well, I'm doing this how many times, right? So if I'm doing something N times, well, that's N times N is N squared, right? And here, like I wrote it out long, we've got 2 plus N times the 1, which would be this, and then the 1N, which is all of this, which then if you multiply this out, we'd see 2N plus 2. But again, all I care about is the N squared because it's the big thing here. And I like to think of this as like something geometric I can put my finger on, right? I've got a number line. This is the same number line as here, right? 0 to N minus 1. So I would put my finger on each of these things. That's what this inside for loop is doing. I need to put my finger on each of these things. So, okay, 1, 2, 3, 4, 5, 6, to N. So I need to do that, and that's N. I need to put my finger on N things. But I'm doing that n times, right? So it's n times n. It's a square, right? So here's a test for you. Ooh, this is a good one. This is a really good one. Okay, before I get to the test, actually, after everything I just said here about T of n, deriving T of n, looking at the code, coming up with T of n and all that, yeah, don't do that. Here's what you do. If you ever see a chunk of code that looks like this where it depends on some scalable n, if you see a for loop, think linear, think order n. If you only see a for loop, think order n. If you see nested for loops, you're going to think n squared. All right? That's like the trick here. And we'll see examples of log in a moment as well. But the trick here is look for loops. Look at the loops. Always look to the loops. How many times is that loop going to run? Is there any more looping inside that loop? So after all of this, because this is the more formal description of everything, your classic lazy computer scientist is just going to go straight to the loops. How many times does this loop run? How many times does this loop run? That's what we're going to do. So with that in mind, have a look at this one. And I'm going to give you a moment on this because this is a good one. This is a good one. I like this one. Because notice it's basically the same as this with one key difference. Instead of j starting at 0, we have j starting at I. So I'm going to give you a moment to think about this one. And I want you to tell me what the big O is of this. And it's easier than you think, but n squared. Well, why n squared? Why are you saying n squared? Oh, n. Interesting. Okay. 2 for loops. Okay, yeah, but you know, like how many times did this loop run? Well, this loop ran 0 to n, right? Where this one, the amount that the inside for loop runs depends on which step of the outside for loop we're on. Because the first time it'll be 0 to n, then the next time it'll be 1 to n, then the next time 2 to n, 3 to n, 4 to n, 5 to n. So every time this loop runs actually a little bit less. So 2 for loops, n times n. All right, so we've got a bunch of different guesses. I'm going to tell you something. N is wrong. And n squared is correct, even though I just ranted about it. But why? Okay. Here we go. The trick here is don't skip the steps. Think about what's happening. I always like to go back to, yeah, but you were right for the wrong reasons. Well, kind of the right reasons, I guess, but yeah. Here's what we're going to do. We have nested for loops. I always like to go back to this. Okay? So here, I'm going to copy this. Copy image, paint. All right, cool. So the first time through that loop. So what I'll do is I'll have the, come on, I wish I could. Really? You won't let me? All right, the first time through, the inside for loop will be the rows, okay? One row will be one run of the inside for loop. The outside for loop will be, well, no, that's the rows. The columns are the running of the inside for loop. Yeah, okay. So one iteration of this is there. Okay, we finished running that inside for loop completely. Then we do it again, but I is now 1, right? So let's think about this. The first time through that loop, I is 0. So j also starts at 0, right? So I would go here, and then j becomes 1, 2, 3, 4, 5, n, right? So I will have run, okay, n times here, right? I had to put my finger on n things for the first time through that for loop, right? Do we agree with this statement? Or any questions about this statement? Because if you do have a question, that's fine. But just remember that it's because j starts at I. Well, the first time this loop runs, I is 0, so j will be 0. And I heard a boop. All right, so I'll assume you speak for everybody. Okay. Next time through the loop, though, I is 1. So j doesn't start at 0. J starts at 1. So we don't actually put our finger on this one. We go here. Yeah. And then, and then this time I'll have run it n minus 1 times, right? I'll have run it n times, but I guess just not that first time. And then the next time, I is 2. So we don't run this, but we run this. Okay, finger there, dot, 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 dot. There. Now we got, okay, n minus 2. Why is it not n minus 1 times n minus 1? Ah, because that's like n squared. Well, first of all, we start counting at 0. So 0 to n minus 1 is still n things. But n minus 1 times n minus 1 is n squared minus 2n minus plus 2n. No, minus whatever. Factor that out. It's the same order. You're right. I forgot to bring my headphones is right. Like, it's the same order. Because at the end of the day, we don't care about the minus 1s. But back to this. Okay, then the next time through the loop, I will be 3. So we start here. We skip these 3 things. So we go there, dot, dot, dot. There. So this will be all n minus the 3 we skipped. And so on and so on and so on. Until finally, we're here. Which will be n minus... I guess it would probably actually go here, right? Whatever. I'm not going to think too hard about this. So this would be like, okay, 1. And then the last time through the loop, it would be n minus 1. So we never actually need to run anything here. So this is like 0. No, that must be 1. And then this must be 2. Let's go with that. So... Yes, because we don't care about the stuff that's not dominant. The dominant part, if you factor out everything there, or factor out, like multiply out everything there, n squared will be the dominant term. So, going back to this, the first time I did n things. Then I did n minus 1 things, n minus 2 things, n minus 3 things, n minus 4 things, and so on and so on and so on. Or alternatively, we can think I did 1, and then 2, and then 3, and then 4, and then to n minus 3, to n minus 2, to n minus 1, to n. Does this look familiar to anybody? Come on, it's got to look familiar to somebody. First thing I'll show you is like, okay, we have this square. That's this n by n square, right? Pretend this is a square. And I'm actually just cutting this square in half. Because the first time it's n, and then like this gets smaller and 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 smaller. But we never actually do anything over here. So this is a square, but it's actually not the full square. How much of this square are we doing? Someone. This isn't a trick question. How much of the square are we doing if we're only doing, you know, like that? Half of it. Half of it. Exactly. We're doing half of that square, right? Because, you know, great. So it's like a triangle. Cool. Now, you probably remember, if I have something that's like, okay, let's make it black. 1 plus 2 plus 3 plus 4 plus ... plus n. What do we call this? Let's do plus n minus 1. Factorial. No, that would be multiplication. These are pluses. Yeah. Come on, we talked about this last semester. We got a special name for this type of thing. It looks like we have a series of numbers, right? And they're being added together. This is a sum of series. Well, it's an arithmetic series, right? Like, that's what we got here. And we might remember, oh, there's that magic formula of n times n minus 1 divided by 2, right? You might remember that magic formula or that like thing that this gets to. And if you don't remember this, that's fine, because you'll always remember it if you go and do what we do, where we go like, okay, I'm just going to double this series and just go, okay, and write it in reverse. So I have n plus n minus 1 plus dot, 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 plus 2 plus 1. Great. So I've doubled the series. Okay, so I have this like n here. There's n numbers there. But then I doubled it, right? So I've got like, okay, now I've got like times 2. Okay, great. And here's what I'm going to do. I'm going to add these numbers together, okay? Or is it n plus 1? Ah, I blew it. I wrote down the formula wrong. I'm going to add these numbers together. What's n plus 1 equal? Someone say it. Someone's got to know what n plus 1 is. N plus 1 is n plus 1. That's great. So here we've got our n plus 1. And then what's n minus 1 plus 2 equal? Yeah, n plus 1. That's great. And then n minus 2 plus 3 is also n plus 1 plus, I'm not writing these things, n plus 1 plus n plus 1 plus n plus 1 dot, dot, dot. And then lastly, what's 1 plus n equal to? Or we can do the other 2, but this is obviously 2 plus n minus 1 is n plus 1. And then a plus n plus 1. How many n plus 1s are there here? How many of these do we have? We've got n. Oh, that's fascinating. So if we have n, okay, if we have n plus 1 n times, well, that's just n plus 1 times n. Cool, but we've got a problem. A moment ago, we just doubled this, right? So we doubled n. This would be the equation of adding this arithmetic series together and doubling it, but we didn't double it. So how do we undo a doubling? Someone knows. Divide it by 2. Oh, yeah. Yay! And then we look at this and go, okay, so this is like 1/2 times n squared plus n. Right? I just took the 1/2 out from here. I multiplied the n in. Do we care about 1/2? 1/2's a coefficient. Do we care? No. N squared and n. Do we care about the thing that's non-dominant? No. Boom. N squared. Yay, right? And yes, I messed up before because earlier I said n times n minus 1 when it's n times n plus 1. I blew that, I guess. What's this? I'm not going to click that right now. But maybe someone can tell me what that is. All right, back to this. So this right here is n squared. So now how about this one? Okay. And the trick here is, think back. This is just a single old for loop, right? 0 to n, but we're counting by 2s. So go back to the number line. How many things are you going to have to put your finger on? Okay, so look at this and tell me if you can figure out what big O of this is. What? Ladies and gentlemen, we got them. We got what? You're throwing me off here. Well, anyways, okay, well, let's focus on course content for a moment, and maybe we'll check the link out later. But what's the big O of this? Obviously, the trick here is like the I equals I plus 2. It's not a trick question, just think of the rules. N. Well, I don't take any half answers because that's not an answer. That's an N. If you're going to give me an answer, oh, okay, N. Why N? Tell me why. It's always N. No. Well, here's why. Because I always go back to the number line. Because plus 2 coefficient type number. Kind of, but what we're doing here is I starts at 0, right? So then I plus 2 is 2. So I put my finger on the 0. Then I put my finger on the 2. I skip the 1. Then I put my finger on the 4. I skip the 3. Then I put my finger on the 6. So I'm counting by 2s, meaning if there are n things in here, how many things in total am I going to put my finger on? Half of them. Not n over 23, half of them. I assume that's a typo. So if you're doing half, 1/2 times n, that's a coefficient. Do we care about coefficients? No. So it's big O of n. Cool. And now for the trickiest one of all. This one. I starts at 1, but I is now I equals I times 2. So what's this one? And I'll give you a hint, right? Think of the number line, but also how quickly will we run out of numbers in the number line? Right? If I have n numbers, that's the hint. I'll give you a second to think on this one, because this one's a tricky one when you first see it. But it's not too bad, I think, once you kind of get a chance to chew on it a bit. Two and the amount of pairs? No. Why? Okay, Spoon's saying log base 2. What do you mean run out? I mean, like, when we were counting by 2s, right? I will run out of things after I've put my finger on half of them. But this is a little different because we're multiplying by 2. So I starts at 1. Let's think of this for a second here, okay? I starts at 1. Okay, so we've got our 1. Then it's I equals I times 2. Well, 1 times 2 is 2. Then that's 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, and so on, right? That number grows really quickly. N to the 2. Well, okay, so this is interesting because the number is growing at n to the 2. So this would be like the indices I'm putting my finger on is like growing at n over 2. But remember, we've got this like limited number n. Let's say n was 1024. Okay? If n was 1024, right? If n's 1024, and it was linear, okay? Let's say it didn't have I equals I plus 2. Let's say it wasn't I equals I times 2. It was I equals I plus 1. Okay, so it was just regular old linear, n. How many things would I need to put my finger on if I was looking at this linearly? N, all of them, right? Yeah, I gotta put my finger on 10, 24 things. But this case is a little bit different because, like, sure, when we saw that when we were counting by 2s, really we were only putting our finger on 512 things, but 512 is just a coefficient, so. Well, here, how many things do I actually put my finger on if n is 1024? Well, I'll put my finger on the 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I put my finger on 11 things, which is a hell of a lot less than 1024. And here's the funny thing. Let's say actually that n is not 1024. Let's say it's a 2048. Right? So I just doubled n. Okay, to 2048. If I'm doing a linear search, how many things do I need to put my finger on now? No. The linear one, linear. If I'm doing a linear, starting at 0, then 1, 2, 3, 4, and I'm going to 1048, what do I need to do to? Yeah, all of them, right? But if I'm taking the... If we have 2048 here, I only need one more guess, which is pretty cool. So the question really is, what's the relationship between the number of steps, the number of things I have to put my finger on, and the size of n? That's the question here, right? When n is 1048, and we're doing it linearly, how many things do we have to put our finger on? All n of them. If n is 2048, and we only look at 12 of them, well, okay, what's that relationship in terms of n? Right? So with linear, when it's n, it's n. When it's quadratic, it's n squared when the input's n. So if our input's n, what do we have here to give us 12? 1024 is equal to, or no, I got this. I may have written these down backwards, and of course it's Friday and my brain's not working all the way. But basically the question is, what's the relationship between 12 and 2048? Any ideas? Some people were saying it in the chat. I just want to see what the question is here, or what the answer is. What do you say? Someone's got to have a good guess here. What if we think about it in reverse? What do I do to 2048 to get it to 1024? You divide it by 2, exactly. So this is a divided by 2. How about to get to the 512? Well, that's another divided by 2. Each step we take here is a divide by 2, 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 a divide by 2. So if I have an exponent, and if I'm saying I want to multiply a number together 7 times. Like I want to multiply a number with itself 7 times, okay? So I would say that would be like x to the power of 7, right? Where's the 7? X to the power of 7 is like, okay, I want to multiply that number by 7. No. I want to multiply that number with itself 7 times. But that's like an exponent, right? That's like the x here. So if I want to multiply like 2 by itself 7 times, I would say 2 to the 7. But I don't want to multiply 7 times. I want to divide 7 times. What is the magical mathematical operation we use to, not square, what's the magical mathematical operation we use to do division over and over and over and over and over? If exponent is multiply over and over and over and over and over, what's the division? What do you mean log question mark? Of course it's log. That's what log is. But of course it's log base 2 because we're always dividing by 2. So log base 2 of n. Exactly. So that's like saying, okay, if I say, no, log base 2 of 2048, well, that means divide this by 2 over and over and over and over and over and over and over, right? So if we keep dividing this by 2, like how many times do we divide by 2? The log is like the inverse log base 2 is the inverse of 2 to the whatever. Okay? So let me prove that to you. Because I realize a lot of you clearly recognize the, let's see if I can go back. You clearly recognize this is the doubling. And the doubling is easier for us because we're more comfortable with multiplication and exponents, right? Because we do it more in school. The division's weird because we're not, I don't know, we all learn log, but let's be honest, we all kind of like wish we didn't, right? So I know you recognize this direction. The point is, yeah, we're doubling every time, but we're doubling in this like finite space. So it's like, how many things are we going to put our finger on? So if we're like doubling our way to the end every time, it's like we're halving the amount of things left every time. The doubling and the halving are inverse operations, right? Let's prove that. Google. Log base 2 of 100 is, wait, let's do 2048. There, we'll get a nice, good number. 11, okay? But if I do 2 to the power of all that, it's 2048. It just undoes it. And then, of course, I could do log base 2 of that, which is rather silly. But, like, they're just inverse operations. They just keep flipping each other. 2 to the power of 12 minus 1. What do you mean? Like, to get the specific number here? Well, yeah, we could talk about the specific numbers. Yeah, 2048. So if you look at the, where's paint? If you look at this, so yeah, we're looking at the number of things we're putting our finger on, right? But remember that really, we don't care about T of n. What do we really care about? Do we care about the, oh, well, really it's n minus 1? No, it's just log base 2 of n. So you're right, Fork, but you're working too hard trying to even get into that precise. All we care about is like, oh, it's log n. This is the tricky one. I'm going to warn you, this log base 2n, this is the tricky one here. Most of the log based, I'm getting tongue-tied. Most of the log base 2 computational complexity we'll see a little later in the course will not be formulated like a loop like this. It's going to be based on recursion, but you'll probably find it a little easier even when we get to that. This is admittedly right here, this example, if I could find it, this example is me looking hard to make a logarithmic one here. So its big O is log base 2n. All right. So after all of that, here's the question I have for you. Here's the stacks, or the linked stacks pop. Okay. What is the computational complexity of this relative to the size of the stack? Size is our n here. So what is the computational complexity of a pop? And this is the linked stack, of course. Why is it n minus 1 for a pop? Yeah, but I'm only doing one pop. I've got a stack of size n, and I'm popping one thing off it. How much work is that? I'll give you a hint. It's not n minus 1. It's 1. Yeah, it's just 1, right? So this here, pop on a linked stack, is big O1. It's constant time. The amount of work a single pop takes does not depend on the size of the stack. But let's look at the array stacks pop. Have a look at this. What's the computational complexity of this? We have a stack of size n. We want to remove one thing. How much work we got? N. Why is it n? I'll give you a hint. It's not. No, it's not. It's not n, and there's no n amount of work. I have an array stack of size n, and I want to pop one thing from it. It's still 1. What are you? You're working too hard. You're looking for more work to do. No, huge mistake. It's constant. Because all we have to do, think about it, right? What do the steps take? Okay, decrease top by 1. Stack at index top is the thing I want to return. Set stack at top to null, and then return the element. None of this depends on the size of n. I love work. No, you don't. Now let's look at push. Here's the linked stacks push. Okay? Our stack is size n. How much work is this in terms of the size of the stack n? How much total work do we have to do here? What's the big O of this one? N. No, it's not. It's 1. See, I think you're just throwing numbers out because you're expecting 1 to be n. Why? Well, we take the element, we create a new node. That's a constant time operation. We take that new element, or the new node, and set it next to top. It's constant time. And then we say, hey, top, you're going to now reference to push. Okay, great. That's constant time. And then we increase size by 1. It's constant time. All of this is constant time. It's not n to the n to the n to the n. That would be bad. Now, what about array stacks push? Look at this code and tell me what the computational complexity of all this is. I'm giving you a big hint with the highlighting. Okay, but you gotta tell me, no, it's not n squared. I think now you're just playing with me, Spoon. It's not 2, it's, and I'm talking big O, so that 1 plus doesn't matter to me at all. So, someone's gotta tell me why. Because expand capacity has to iterate through the whole array to copy everything over. Well, and the stack length is what n is here, right? So if our stack is size n, let me put it this way. Let's say our stack size, our length is, oh, I see. When you said stack.length, it depends on stack.length. Oh, okay, R2, T2. I see what you're saying. And yes, you're right. Because if I have a stack of size, let's say my array, where I have a capacity of 10, how many times do I get to use push and it's only constant time work? 10, right? Because it's that 11th time. At that 11th time, I try to push. I need expand capacity. So the trouble here is expand capacity is the thing that's linear. Why? Well, we make a new array, and then we use this for loop to copy everything over from the old array to the new array, and then we update what stack references. So expand capacity is linear. Expand capacity is order n. And we often really like to talk about, well, you know, we always care about the worst case scenario. And the worst case scenario here is, well, we got to call expand capacity. So here we would say, even though, you know, it's only doing it once every 10, you know, it's still the worst case scenario. So this right here, it's linear. Okay? So this right here, it's linear. Now, if you know that, which implementation would you want to pick? The linked stack or the array stack? The linked stacks push is order 1. The array stacks is, I guess it looks like it's order n. The link one, right? Because it doesn't take as much computation time. Well, although everything I said is correct, we could be a little bit more correct here. And there is an aside here about amortized time complexity that goes on to say, in very special cases, if this will in fact load, in very special cases, we can actually kind of like, my internet's been weird today. It's like, you can all still hear and see me, right? Topic 9, amortized. Well, that's unusual. Okay. Let's try that one more time. Nope. Okay, so apparently that's not working. Well, anyways, I'll try to explain this without it. You know, if I have a capacity of my... Here's a thought experiment. The capacity of my array is X. Okay? So I have X spots in it. So if I have X spots in that array, how many times can I push onto my stack and have it be constant time? I have X spots in my array. How many times do I get to push where it's constant time? X. Yeah, I get to push X times where it's constant time. But on that next time, on that X plus 1th time, I have to do expand capacity. And expand capacity, how much work is that expand capacity if my capacity that is full is X? How much work is expand capacity? X, right? So it's like, well, that's big, that's linear, order n, well here n is X, so it's, you know, it's linear, right? So think about it like this. If I have, let's go back to paint. If I have this, you know, I really wish that that aside would load, because it does a decent job. Okay, it's working now. I don't know. Here we go. So here I'm replacing, oh, no, X with N. I have a capacity of N. So I get to put my finger on each of these things that I get to push at constant time. But on that nth time, I need to do an expand capacity, which takes order n time, right? But I can kind of like pretend that it's like, well, you know, I got all these constant time things, and then once after n, I have to do n things. What if I kind of like amortize that work and pretend I'm actually like doing all that work over, like averaging all that work out on that nth time? If I take that, all of that work that would have to get done between 0 and n, right, because of this, and I average it over every single push I do, I could kind of think of it like this, right? Where it's like, well, actually at each step, it didn't take 1 step, it took 2. But 2 is just like a constant, so who cares? So, no, you're thinking, no, well, you guys are trying so hard to work hard. Get integrals out of here. I never want to see anything like that in here. So, it's like, I can pretend, like, look, if I did, I realize we're like basically out of time, but let's see if I can whip this together real quick here. If I have n times 1 amount of work, and then on that last time, on that nth one, I have to do n work. So I have to do 1 thing of n work, right, times n, right? This is my expand capacity. I get to do n constant time things, and then at the end of that, I have to do 1 thing that takes order n. This is the expand capacity I do once for every n things of order 1 I do. But if we add that all together, it's like 2 times n plus 1. No, or times 1. Right? And so that's like 2n times 2, but I mean, I don't care about, you know, we don't, who, like, who cares? So, no, stop that. Point being, we can amortize it and pretend it's still linear. So there you go. So we could say like, oh, it's still linear. Sure, we know that we need to do that expand capacity every once in a while, but it's so infrequent that we spread it all out. Anyways, I'm going to end because I'm now over time. But there you are. And have a great weekend.